The Evolution of Materials and Manufacturing Techniques of Jet Engine Turbine Blades by Katie Bernhardt. Engineering is usually defined as the designing and building of machines, engines, and structures. However, people tend to overlook the grand aspect of redesigning and re-engineering. The reason planes, iPhones, and computers look and work the way we know them to is due to the constant desire and need for the next best thing. Imagine trying to fly from New York to California in the Flyer designed by the Wright brothers. You wouldn't make it to the next block. Every small part of the Wright brothers' plane has gone through some type of evolution, especially the main component in making a plane fly, the engine. This is a commercial plane engine. There are thousands of parts that go into developing it. Inside of the engine is a turbine. The turbine is located behind the combustor near the end tail of the engine. The combustor is used to ignite jet fuel mixed with air to create thrust. The turbine blades spin behind the combustor to push the hot air through the engine, cool it down, and shoot it out with enough force to lift a commercial plane into the air. Due to this heat and pressure on the turbine blades, they need to be able to withstand the stress it is put through. This is when the re-engineering comes in. The first attempts of developing a jet engine were very limited due to the lack of materials able to withstand the heat and pressure required to make a plane fly. Then, in the 1940s, the superalloy became the material of choice. A superalloy is a metal made by combining two or more metallic elements to give strength to the final product. The turbine air blades are nickel-based with other materials mixed in. The air melting process used to create the superalloy blade included aluminum and titanium elements, strengthened material, however, creating low ductility. For a blade to work successfully, it needs to be a combination of strength and ductility. That is when, in 1953, the innovation of vacuum induction melting, or VIM, made the jet engine what it is today. VIM uses magnetic currents to melt metal. The metal is melted with a current, then molded into the blade. VIM boosted alloy capability by 200 degrees Fahrenheit. This process continued for about 5 years, until, in 1958, vacuum arc remelting, or VAR, produced large forgings for discs, shafts, bolts, and structures, such as a turbine blade. VAR goes through the same VIM process, but then remelts a portion of the material and cools the material at a controlled rate. Finally, in the 1970s, hot isostatic pressing, or HIP, was discovered. HIP exposes the superalloy to elevated temperatures and high pressure. This process reduces porosity and increases the ductility and fatigue strength, just as the turbine blades need to be successful. However, the innovations didn't stop there. There have been 3 different ways to manufacture an engine turbine blade with the HIP: equiaxed casting, directionally solidification, or DS, and single crystal, or SC. Equiaxed castings are crystals that have axes of approximately the same length without any order. This type of casting creates grain boundaries or defects in the material and can form failure points. Due to these failures, turbine blades began being manufactured with DS. DS arranges the crystals in layers, eliminated some of the grain boundaries in the tensile direction or the vertical direction, but not in the horizontal direction, improving the thermal fatigue, but not to the extent needed. However, SC took it one step further. This process allows for a coating of a blade with one single crystal. One single superalloy crystal completely eliminates grain boundaries and allows for a material with the capability to withstand a great amount of stress for much less strain than ever before. Realizing that no matter how the turbine blade was formed, it still melted at about 24 degrees Fahrenheit, engineers had to figure out an aid for the material to withstand an even greater temperature. The next step was to develop a coating to prevent oxidation and melting. In the 1970s, as the superalloy development proceeded, aluminide coatings were being added to the blades. This thermal barrier coating increased the blade's capability to resist the constant heat. Even greater than the aluminide coating, ceramic thermal barrier coatings were being applied to the blade, starting in the early 1980s. This coating is applied to the outside of the blade and increases the blade's ability to endure heat by 400 degrees Fahrenheit. The final addition to the blade was an air cooling system. This is a series of holes in the blade, allowing for air to flow through. This cuts down on material usage, and the airflow helps to cool the blade. Now, it's clear to see that the turbine blade you see today is nothing like what you would have seen 80 years ago. But it's not just the turbine. It's the engine, the wings, and the entire plane. So next time you fly from New York to California, think of the engineering and re-engineering it took to get you to your destination.